All right, so on Thursday last week, we were talking about alternating series. And we saw that there was a test for an alternating series that was actually pretty routine. An alternating series converges if the magnitude of the terms are going to 0. That's basically it. So we had to do two things. We had to take the limit of the series and make sure that its limit was 0. And then we had to check that the terms were shrinking in magnitude. So that's what we did last week. And I mentioned that the one remainder, we saw some remainder ideas that were a little complicated. The one remainder that we're going to look at in detail is for the alternating series. The alternating series is a pretty easy type of series to try to get a handle on the remainder. And so what I have here is a graph of an alternating sequence that converges, and I've got a picture of the partial sums. And so what I want you to think about is that if you have a convergent series, you can think of it into two parts. You can break it into two parts. S sub n is the sum of the first n terms, and then the rest is called R sub n. So if the series converges, we can write the sum as the sum of the leading terms plus the sum of the tail. So the remainder is basically the sum of the tail. And let's look at this picture. So this alternating series is going to converge to whatever this S value is. And S sub n is whatever this number is right here. Well, if we went and added the next term, if we added a sub n plus 1, that would be the next term, and that's what's in green. That would be a negative number. It would take us down to here for S sub n plus 1. And then if we added the next term, which would be a sub n plus 2, that's a positive number, which would bump us up above the eventual sum. And then if we added the next term, that would be a negative, and it would take us down to here. So you can see the sequence of partial sums is oscillating around what the eventual limit is going to be. And it should be pretty easy to see that the distance right here, this is the remainder. So S sub n is here, the sum is here, that distance right there is the remainder. And the remainders, when I put that little information here that this is R sub n, I'm talking about a positive distance. That distance is positive. Okay? If we're here at S sub n plus 1, then this is the remainder, right? The remainder is the difference between the partial sum and the actual sum of the series, the eventual sum. All right, so you can see there's the remainder. There's the remainder for this partial sum. And similarly, there's the remainder, that distance. You can see the remainder is going to 0. This is a convergent series, so the remainder should be getting smaller and smaller as we go out. But notice this, that the next term in the series, if we look at the magnitude of this green line, isn't this positive distance more than that positive distance? Right? And similarly over here, this positive distance is more than that distance right there. So what we can say is that the magnitude of the next term gives us an estimation for the remainder. Right here, there's the remainder for S sub n plus 2. Here's the next term. That's bigger than that, distance-wise, just think distances. That's bigger than that. So we can use this as an estimate for the remainder. So that's what we're going to do with alternating series. Instead of looking at crazy integrals going from n to infinity or n plus 1 to infinity like we saw last Thursday, we're just going to look at the first unused term. The first unused term is going to be a gauge on the remainder. So the remainder could be positive or it could be negative, depending on whether your partial sum is above or below the actual sum of the series. So the remainder could be positive or negative. And if we take the absolute value of the remainder, that's always going to be less than or equal to the magnitude of the next term. And remember that with an alternating series, the a sub n's are always positive. So when we look up here, yes, we are going down to get to the next partial sum here. the a sub n plus 1 is positive, but the sign in front of it is negative, which means we subtract it. But the actual sign of the a sub n's is always positive. Okay. All right, so that's it. The remainder for an alternating series is the magnitude of the next term. So let's try some of these. We want to figure out how many terms have to be added together. This is a convergence series. They tell us what these converge to. That's kind of irrelevant here in a lot of ways. But these are series that have known limits, known values, and we want to have the remainder be less than 10 to the negative 4. So this is what our calculator is doing. Our calculator is figuring out if your screen has 8 digits in it, we want to have a remainder that's going to be beyond that screen so that what you see in the calculator is accurate. And so the calculator needs to know, oh, how many terms should we add together for this series to get the accuracy that we need? All right, well, this is going to take some bookkeeping here. We've got to be very careful about this. So when we are writing this series, let's write out a bunch of terms and see if we can be very careful with our bookkeeping. So when k is 1, that's even, so it's positive. The a sub n is over here, though, right? The a sub n does not include the minus. This is the switch. This changes the sign. But this part here, that is a sub n, or a sub k. That is not including the minus sign. All right, so the first term is going to be positive 1 over k, 1 over 1 in this case, so it's 1. And then minus 1 over 2 plus 1 over 3. This is the alternating harmonic. And then we're going to go like that. So this is the number of terms. I'm going to put both k and the number of terms here. So k and the number of terms, which a lot of times we use n to represent the number of terms. And in this case, they all match, right? Because this starts at 1. So what we're going to need to do is keep on going, and let me point something out. If we were to add these two numbers together right here, that would be called S sub 2, because we've added the first two terms. That's S sub 2. Okay? And S sub 2 is within 1/3 of, because we know this series converges to natural log of 2, we would say that S sub 2 is going to be within 1/3 of the sum of the series. All right, the first unused term is what we are going to use as our gauge on the remainder. So the remainder is less than 1/3, which means this sum of the first two terms is going to be within that distance of natural log of 2. If we added up the first, say, let's get a different color. So let's suppose we added those up. What number is that going to be designated? S sub what?
4.
S sub 4. We've added the first 4 terms together. So the purple is S sub 4. S sub 4 is within how much of natural log of 2? What's the 1/5 would be the next term, the first unused term, the first neglected term. So we'll be within 1/5 of natural log of 2. Okay, so that's kind of what we're thinking in our mind. We just have to look at the next term. That's going to be our error estimate, our remainder estimate. Okay, so now we're cruising along here, and when we plug in, let's see, so let's get to k equals n minus 1. So because k starts at 1, the k value and the number of terms is matching, and then we're going to get to the nth term, and then we're going to get to the n plus first term. So I'm just sort of looking at what the term value looks like. So at n minus 1, we're plugging in an n minus 1 there. So we get 1 over n minus 1, and then we're going to get a 1 over n, and then we're going to get a 1 over n plus 1, and then etc. So we don't know the signs in here. Like these signs, because we don't know if n is even or odd, we don't know if it's plus or minus. So we don't know exactly what this sign is. So there's going to be a sign here, plus or minus. There's going to be a sign here, plus or minus. Let's just assume that n is going to give us that. It doesn't matter, though, because when we look at the remainder, we don't include the minus. Right? It's just the magnitude of the term. It's just the a sub n part. So this could be plus minus plus, or it could be minus plus plus, or minus plus minus. Doesn't matter. OK. Now, we want the remainder to be less than 10 to the negative 4. So what we're trying to do is figure out what n has to be to get this 10 to the minus 4 value. So here's what we want. We want our 1 over k. We want that to be less than 10 to the negative 4, which we're going to write like that. So if we can figure out when this is true, that's what we want to know. Then we want to add up everything in front of it. So S sub 4 is going to be within 1/5. We want that number to, we want the first unused term to be less than 10 to the negative 4. So we want to figure out, well, what's the k that's going to give us a value less than 10 to the negative 4? So we multiply both sides here. So we have 10,000 cross multiplying. So k has to be greater than 10,000. And we want the first k value that makes this statement true. So what does k have to equal? 10,001. That's the first k value after 10,000. So when we come out here, when our k value is 10,001, that is going to be the term that is under or less than 10 to the negative 4. So we want to add up everything that's in front of it. If we can find the first term that's under 10 to the negative 4, then we add up everything that's in front of it. So what we need to do, let me just want to add a little bit of space in here. So what we need to do then is ask ourselves what we're going to add together. So how many terms are we going to add together? If when k is 10,001, so when this is 10,001 in the denominator, that term's going to be less than 10 to the negative 4. We have to add everything in front of it. So how many terms are in front of that? 10,000 terms. So let's rewrite this in a way that kind of clarifies that. So if we look at our sums, if we look at the partial sum, we're going to do this. So this is what it's looking like. And then when we get to, say, 10,000, 10,000 is an even number, so we're going to have a minus in front of the even, so minus 1 over 10,000. And then plus 1 over 10,001. And then minus 1 over 10,002. And that pattern goes on forever. So that's what our series looks like. And we just said that the very first term that's under 10 to the negative 4 is that. That term is under 10 to the negative 4. All right, so we have to go out to 10,001 for k, which matches the number of terms. So we need to add everything in front. So this is what we want to add up. And this is S sub 10,000. That's the sum of the first 10,000 terms. So if we add up these 10,000 terms, the next term is our gauge on the remainder. The next term is less than 10 to the negative 4. So we want to add up all those. So this says how many terms do we need? So our answer is 10,000 terms. So that's what we want. 10,000 terms. Okay. Let's try another one. So we're going to take a few of these to get used to the process. So let's try to be diligent here. This one starts at 0, so we've got to be a little more careful. So if we start looking at the terms, we know that our goal is that we want this piece to be less than 10 to the negative 4. We want to know what's the k value that corresponds to that being less than 10 to the negative 4. So we set up an inequality. So we say, all right, we want 1 over 2k plus 1 to be less than 1 over 10 to the 4th. We cross multiply. So we have 10,000, we have 2k plus 1 over here. We subtract 1 and get 9,999 less than 2k. We divide both sides by 2. And we want the first k value that satisfies that inequality. What is the first k value that satisfies that inequality? So if you type into your calculator 9999 divided by 2, what's the first integer above that? 500. Do you agree, Danny?
5,000.
I agree with that.
Sorry.
5,000. 5,000. So this tells us that k has to be 5,000. So that's the first k value that satisfies that inequality. Type it into your calculator, you get 4,999 point whatever, 0.5, and then that's going to be the first positive integer that's above that. So that's when k is 5,000. All right, so let's take a look at our terms here. So our terms, let's say our series, when we plug in 0, we get a positive here, so our first term is 1. So let's put down here the k value. So the k value, when k is equal to 0, right? How many terms is this? So I'm going to use this number symbol to represent the number of terms. That's the first term, number of terms. Then I plug in k equals 1, and then 2, and this is going to be 2, and then 3. Okay, so when we plug in k equals 1, this is odd, so it's negative. Plugging in a 1 right here, we're going to have 2 plus 1 is 3. So this is going to be minus 1/3, and then plus. Plugging in 2 is going to be a 5 down there, so it's going to be 1/5. All right. Now, we're trucking along. And let's plug in, this says when k is 5,000. Let's go a little before and a little after. So what about when k is 4,999? First off, is it going to be positive or negative when we plug in k equals 4,999? Positive or negative? So when you plug in an odd number, you're getting a negative. So we're going to have a negative, and it's going to be 1 over, we've got to take that number, k, and plug it in here, and what do we get when we multiply that by 2 and add 1? Somebody type that into your calculator or do it in your head if you're, so it's 10,000 minus 2, which is 9,998, but then 1, so 9,999?
Mm-hmm.
So 9,999. And now we're plugging in the next k value, which is 5,000. When we plug in 5,000, it's going to be positive. So it's positive. And then same thing, plug in the k there. Double that, get 10,000, add 1, we get 10,001. 10,001. Next term is going to be negative. We've done enough of those, I think. Okay. So, when k is 5,000, right here, this term is less than 10 to the negative 4. So this is, the term has value less than 10 to the negative 4. So that is our remainder term. We get to there, that's finally less than 10 to the negative 4, we add everything up in front of it. So we want to add, well, come on. I was hoping this pen was going to not do that jumpy thing. Trying to find a pen that is less likely to jump. So we want to add these. Right. So how many terms is that? Well, let's come down here. This is our counter. This is counting the number of terms. So we have to look at the pattern. So from the k value, we add 1 to get to the term value, the term number. So we add 1 here. This is 5,000 terms. This is going to be 5,001 terms if we were to add all those. This is the number of terms we want, so our conclusion is therefore 5,000 terms. And this, when we add these up, what would that be called? S what? S sub?
4,999.
S sub 5,000, because S sub 5,000 means the sum of the first 5,000 terms. The k values would go from 0 to 4,999. But it would be S sub 5,000. S sub 5,000 means the sum of the first 5,000 terms. Okay, starting to get it? A little bit of a, ask a question if you have one before we try the next one, because we'll do 4 of these, but it takes a little bit of practice to sort of see what's happening. Our general principle, find the term that's smaller than the error, add everything in front of it. The hardest part is keeping track of the term numbers. Okay. Same rule here. So they tell us what this series converges to, which we don't really need in this case. Once again, we want to know how many terms do we add together. Let's make this more complicated by starting not at k equals 1. When we start at k equals 1, that's the easiest scenario because k and n match. Let's make it harder. Let's make it harder on ourselves. So let's just suppose this is k equals 3. Okay? Make it a little bit harder. So when we come out here and we start, the actually, I don't want to put equals there. I just want to write the partial sum down here. So let's see. This is going to be even up here. 3 plus 1 is even. So it's going to be 1 over 9. That's our first term. So the k value here is k equals 3. So k value is there. That's k equals 3. The number of terms, 1. Right? We've got 1 term there. Next term, we put in a k equals 4. That's odd here, so it's going to be negative. 4 is that value. So that is when k is equal to 4, we now have 2 terms. Number of terms, 2. Next k value is going to be 5. That's going to be the 3rd term. That's going to be positive. We're plugging in a 5, so we get 1 over 25. Minus, etc. Okay, so that's what it's looking like. Now, we need to figure out what k has to be. So we want 1 over k squared to be less than 1 over 10 to the 4. So that's what we're trying to solve. We want to know, hey, what's the k value? So we know that when we cross multiply, we are going to have 10,000 on the left, and we want k to be bigger than 10,000. Oh, that's k squared, sorry. K squared, so we want that. Everything's positive, we can take a square root. Square root of the left side is 100. Positive square root of that's k. So what's the first k value that we have as a solution? K equals 101. That's the smallest k value that satisfies the inequality. So we're trucking along here now. And we want to get to k equals, let's go a little bit before that. So let's suppose we did 99 and k equals 100 and then k equals 101. All right, so we're going to plug in those k values. So when we come up here to our series, this is odd. When it's odd, it's positive. So this one's going to be positive, this one's going to be negative, this one's going to be positive. This is going to be 1 over 99 squared, whatever that is, we don't care. This is 1 over 100 squared. This is 1 over 101 squared. And then the series is going to continue. So that's what the expansion of the series looks like. Any questions up to that moment? So we figured out our k. The first k that's going to have a term magnitude less than 10 to the negative 4 is when k is 101. So k is 101 right here. So that means that this term is less than 10 to the negative 4. So we want to add everything in front of it. So we're going to add up all of those. And the question is, well, how many terms is that? Well, here is our counter. So let's figure out what the pattern is. So we subtracted 2 to get to the term count. So we subtract 2, this is the 97th term. This is going to be the 98th term. So we're going to add up the first 98 terms. So our answer is S sub 98. That's our answer. This means 98 terms that we added together. So we're adding up the first 98 terms. And that's what S sub 98 means. The k value started at 3, ended at 100, and the error is provided by k equals 101. So what this means is that S sub 98, the sum of the first 98 terms, we are within 1 over 10,000 of this number. This is the sum of the series. We are now within 1 over 10 to the negative 4 of that number. Okay. Now whether we're a little above it or a little below it, we could think about and figure out, but don't really care here, but you could. All right. One more. So you guys start with this inequality. Start with, we'll keep this starting at 0, so figure out the solution to this inequality. What is the k value, the lowest k value, that satisfies that? So find that k value before we do anything else. Let me know if you're stuck on it, if you need a little jab. Who's got the first integer k value that satisfies this? K equals 5. What'd you end up with? 5. 5? Let's see. Well, let's see. That one, I don't know anyone that's going to be able to do that one in their head. You're getting, so I'm hearing different numbers. So let's find out. Go to Desmos. You don't always need a calculator, but sometimes you do. So we have 10,000 raised to the third power minus 1 over 2. I'm getting 11.
Do you always want to round up for these types of problems?
Yes.
Okay.
Yeah, always rounding up because so here if we chose 10, we wouldn't be less than 10 to the negative 4. Like if you type in 10, like we want k to be bigger than this number. So we always are going to, it's not even really, we're always rounding up, but we're not really rounding. We're choosing the first k value that's bigger than this. You know, like if you rounded 10.27, you'd round it to 10. Right, but we're going bigger, so we're rounding it up. Rounding is not probably the most correct word, but we're choosing the first k value that satisfies this would be k equals 11. So k equals 11. So now we know what k has to be. That may or may not correspond to the number of terms. The number of terms may be one less than that. It may be equal to that. We have to look at the pattern. So let's take a look. So our terms, let's come down here. We'll write out the series in expanded form. When k is 0, that's going to be positive 1. We're going to get a 1 and then a minus. When k is 1, we're going to get, what's 2 times 1 is 2, 3 to the 3, which is 1 over 27. And we don't really even care. So this is when k is 0. This is when k is 1. So our counter, the number of terms, there's 1, there's 2, and then we're coming down here, k equals, let's do a couple around k equals 11, so let's do k equals 10, let's do k equals 11. Maybe we'll stop there, that should be enough. So the counter is going to be 1 more than the k value. So let's see what we have here. When we have an even, this is going to be a positive, and then when we have an odd, it's going to be negative. So when we plug in 10 up here, 10 times 2 is 20, so we have 1 over 21 cubed. I did my math right. And then when we plug in 11, we're going to have 23 cubed. So looks like that. You know, and this goes on forever. But this is the first term that's less than 10 to the negative 4. When k is 11, this inequality is going to be satisfied for the first time. So if you plug in 11, that gives us our remainder estimate, our error estimate, however you want to visualize it. And then we want to add up everything in front of it. So we're going to add these. How many terms is that? 11 terms. Happens to match the k value here. Not always the case. This is the key right there. That's the number of terms that we're adding together. We're adding the first 11 terms. So 11 terms, which is S sub 11. S sub 11 means the sum of the first 11 terms. That's what it means. So the S subscript is related to k, but it's not k. We always start our counter at 1. First term, 1. Does not necessarily mean k is 1, though. Okay, so this is the error thing that we're going to look at in the most detail. You in other classes are going to do all sorts of other types of error approximations, but in this class we'll just focus on the alternating series. All right, any question on the process here? There's different ways to do this.
Quick question. Could you explain where the 10 to the minus 4 is coming?
Given.
Oh.
So they have to tell us what the accuracy is that we want. They've got to tell us. So we can't figure out how many terms that we want to add together unless we know, oh, we want to add, terms up so that the error is less than 10 to the negative 4, 10 to the negative 6, 10 to the negative 2. So they have to tell us what our threshold is.
And that error, does that refer to the remainder?
Mm-hmm. It's an estimate on the remainder. So we want to go far enough out in the series so that our estimate for the remainder is less than 10 to the negative 4. Because what we've seen with the alternating series is that this term here is just an estimate, that the remainder is actually a little less than it. That this is an overestimate for the remainder. But we know for sure that if we add up these, our estimate for the remainder will be less than 10 to the negative 4, so we're within 10 to the negative 4 of the actual sum of the series. We can't find the remainder exactly because there are ways, I guess in this particular case, we could add up these and then subtract it from there because we happen to know the sum of the series. In real life, you don't know the sum of the series, so you couldn't do that, right? You don't know this number. But what we can say, because we do know that number, is that when we find S sub 98 here, we're going to be within 10 to the negative 4 of this number. And down here, we're going to be, when we add these first 11 terms together, we're going to be within 10 to the negative 4 of that. But we usually don't know that number. Like you could find the actual remainder in these cases because you happen to know what the series converges to, which is very rare. In practice in the world, you won't know what it converges to. But if it's alternating, you can always find an error by looking at the first neglected term.
So should we, at this point, know how to calculate the sum of the series?
No. Yeah, no. Yeah, finding this is very, very, very hard. Yeah, finding these values you would not even do in a master's degree in math. Yeah, no, that's very tricky. Very, very tricky. And that's why we have so many of these tests for remainders, because it's actually very hard to figure out sums of series. So we have a slightly new concept between types of convergence. So up until this point, up until we got to alternating series, we have been dealing with series of positive numbers. Okay? And a series either converged or diverged. Now, if you have an alternating series, some of the terms are positive, some of the terms are negative. So if you think of some of the sort of visualizations, like pumping up the ball or whatever, you're pumping it up, but then you're letting a little bit of air out because you're subtracting. So you've got that kind of thing where you're taking away, some of the terms are taking away from the cumulative sum. And if you have a series that does have negative terms, could be alternating, but it could also be sporadic. You could just have patches of negative terms. But if there are some negative terms, there doesn't have to be a pattern to them. One thing that we will look at is taking the absolute value of all the terms. So if you have a series that has some negatives, and then you decide, okay, I'm just going to make everything positive, so you're going to take the series of absolute values. If that converges, then the original series is going to be said to converge absolutely because you turned everything positive. You took the absolute values, and it still converged. Then we're going to call it absolute convergence. So if you force all the terms to be positive and you still get convergence, we're going to call it absolute convergence because the series of absolute values converges. If the series of absolute values diverges, but the original series converges, then we call that convergence conditional. In other words, you need the subtractions to get convergence. And the classic example of this is the harmonic. So when we look, I should say the alternating harmonic. So when we look at this alternating harmonic, we have come to learn that that converges to natural log of 2. But if you take the series of absolute values, you get the harmonic, which through the integral test, we showed that this diverged. So the alternating harmonic is called conditionally convergent because you really need those minuses to keep the sum from exploding. You have to be subtracting a little bit every other term. If you don't do the subtraction part of it, then the series is going to diverge. So this series is conditionally convergent. You need to have those minuses for convergence. Here's a flow chart, shows if we've got some infinite series, could have positives and negatives in it. If it diverges, it diverges. There's only one way to diverge. You can't absolutely diverge. You either diverge or you converge. And if you converge, you can do it in one of two ways. If you have negatives in there, you could converge absolutely, or you could converge conditionally. If you have only positives, then it's really, it's moot. If you have positives, it converges or diverges. Now there is a theorem here that says if the series of absolute values converges, if you take away the absolute values, the series must converge still. So if you have the series of absolute values, so you've got all positives and you get convergence, if you throw in some negatives, it's still going to converge. Right? If you take a little bit away, you can't force it to diverge. So if you've got a series that converges, everything's positive, but then you sprinkle in some negatives, you still have to have convergence. Can't be divergent. So if the series of absolute values converges, then the series without the absolute values must converge. And similarly down here, this is the contrapositive. If the original series diverges, and then you force everything to be positive, that's still going to diverge. And if it's divergent with the minuses in it, and then you force all the minuses to be positive, it still has to diverge. It can't get smaller. It can't converge. So, conditional and absolute convergence. So let's look at some of these. And again, we're in a situation where the math should confirm our intuition. We need to be generating intuition that is accurate. And we should know ahead of time with most of these whether we're going to get absolute or conditional convergence. Like when we just look at this without the minus sign, in other words, take the absolute values, that's a p-series. And that p-value is 2/3, which is less than 1, which corresponds to divergence. But this is an alternating series, and this alternating series should converge because the terms are going to 0. So we should see that this is a convergent alternating series, and if we take away the switch, we are going to get a divergent p-series, so we should know that we're going to get conditional convergence. So the alternating series convergent piece, remember, for an alternating series, you ignore the switch. And to do the alternating series test, the limit of this has to be 0, and the terms have to be getting smaller. And they will be here. So it's going to be a convergent alternating series, and if we take away the switch, we have a divergent p-series. Okay, but that's not the math. So first, let's show that this is a convergent series. So we're going to use the alternating series test to show convergence. We have two pieces. We take the limit of a sub k as k goes to infinity. So that's the limit of 1 over k to the 2/3. The minus sign has nothing to do with a sub k. The minus sign is separate. A sub k is positive. And this limit is 0. So that checks. Second part of the alternating series test, we want to show that the terms are getting smaller. So we want to show that. So if we're at a sub k plus 1 is the next term, we want to show it's littler, it's smaller than the prior term. So let's see if we can do that. So a sub k is 1 over k to the 2/3. we want to show that this inequality is true. We don't know if it is. So we do that. Cross multiply. And once we've cross multiplied, it starts to unravel pretty darn quickly. So everything is positive, so we can take square roots, we can take cubed roots, we can do whatever we want. We can raise both sides to what power?
3/2.
3/2 power. So we could take, so if we raise both sides to the 3/2 power, isn't that going to eliminate these exponents? So we are, and if you wanted to break it into two pieces, you could say, hey, let's cube both sides to get rid of the denominator in the exponents, but then let's square root both sides to get rid of the 2. And so that's going to lead us to exactly what we want. We're going to get k plus 1 is greater than k. And you, at that point, you could make your conclusion. You can always go down one more step, so therefore true. So that checks. Ooh, slow down. So that checks. So this tells us that we have a convergent alternating series. So the series, as presented, the series a sub k, converges. Alternating series test. Once you have an alternating series that converges, then you say to yourself, well, does it converge if we take away the absolute value? If we take away the minuses, if we take the absolute value? So part 2 of this, we say, let's consider the series of absolute values. So k starts at 1. So this is the series of absolute a sub k. K starts at 1. And here we identify the p value, which is 2/3. So make sure you write that down. That's how I know you know it's a p series. And then you compare it to 1. It's less than 1. And then you make your conclusion. We know that for a p series to converge, p has to be bigger than 1. If p is not bigger than 1, you have divergence. So this diverges. So now we have divergence for the absolute values. We have convergence for the series with the minuses. So our big conclusion is that we have conditional convergence. So that is our big conclusion there. So we need those minuses to keep it from diverging. The minuses are essential. All right, so I want you guys to try this one. I'm going to rewrite it first so that the switch is separate from the a sub k. So minus 1 to the k. So we're taking out the minus 1 to the k, and then we have 1/3 to the k. K starts at 1. All right, so first, consider the alternating series part of it. So use the alternating series test to show that this series either converges or diverges. So use the it's an alternating series. So let's go ahead and use the alternating series test. There is another way, we'll talk about that in a minute, but first I want to make sure you can do it with the alternating series test. Let me know if you have a question on either part of the alternating series test. There's 2 parts to it. Muscle flutter. Good flutter. Do you want to do it? this is. That's okay. Yeah, we just have to shrink this. We have to shrink this here. Is that much? Shrink that. And then go to. Scroll. Then alternating series. Right there, ASD. So the alternated series test has two parts. Limit of base of k is 0. Yeah.
Question.
Yeah.
So why not taking is my
So this is false.
that's false.
So think about, so right here you have a number that's less than 1
Right.
being multiplied by itself.
How is it?
Yeah, yeah. Third times a third is a ninth.
Right.
A ninth times a third is a 27th. So with the alternating series test, this is your a sub k. And what is the limit of a sub k as k goes to infinity?
0.
So as k goes to infinity, 1/3 to the k goes to 0. So that's also known as the divergence test. And we do that first because if that limit is not 0, the series has to diverge. The only way you can have a convergent infinite series is if you're adding numbers together that are very tiny. So the limit of them has to be 0. If the limit of a sub k is not 0, then you get infinity when you add them all together. So that's our first step. And the second test we want to show, or second part, we want to show that the terms are getting smaller. So we want to show this. Well, a sub k is 1/3 to the k. We don't know if it's less, we don't know if a sub k plus 1 is less than yet, so now we do a k plus 1 over here. Okay. There's a couple of things we could do here. You can rewrite this as 1/3 to the k. This is several ways, whatever works for you. So I'll do it this way. And then we're going to cross multiply. And again, there's a couple things. You don't have to cross multiply. You could do something different. Now I'm going to divide both sides by 3 to the k. So if you divide both sides by 3 to the k, on the right, you get 1. How about on the left?
You have 3.
3. 3 to the k plus 1 divided by 3 to the k, you get 3 to the k plus 1 minus k, which is 3 to the 1. So you get 3. And that is true. So both of those two things are true. So therefore we have converge for the a sub k's. So the original series is a convergent alternating series. Now I said there was another way to look at the convergence of this series. And the other way is to recognize that this is a geometric series. And this geometric series always has that exponential flavor to it. The k is in the exponent position. The r value here, so this is an or, you could say that the absolute value of r is equal to the absolute value of this, which is 1/3, which is less than 1, which means convergence. So you could think of it as a geometric series also.
Which is kind of what you do for the second part anyway.
Second part, we're gonna when we
Absolute
look at absolute convergence. Yeah. So let's consider the absolute convergence piece now. So let's come over here, and the series of absolute values is going to give us We're taking the absolute value, so we have really no other way to show that this series converges. We have to recognize that it's geometric. It's not a p-series. So usually when we're doing these, we're going to get a p-series or a geometric series, something that we can tell pretty quickly whether it converges or diverges. And this, the way I know you know it's a geometric series is that you identify R, common ratio. I mean, you could even say that it's a geometric series. But you have to identify R if you have a geometric series. And R less than 1 means convergence. So now we have convergence of the original series, convergence of A sub k. We also have convergence of the absolute values. So what is our ultimate decision then?
Absolute convergence.
So we have, when we think about convergence, could be absolute, could be conditional. This is absolute. So therefore, we have absolute convergence. Any questions on the concept of absolute or conditional convergence? Or any questions on the process? So we're going to do this side first. We do the convergence of A sub k first, because if this diverged, then there's no point in trying to figure out whether it's absolute or conditional. So if you came down here and you concluded that your original A sub k series diverges, there's no point in taking the absolute values because that's just going to diverge worse. So we always want to do that first part. Do that part first. All right, so absolute and conditional convergence. We've got a series here that first we want to show that it converges. The series of A sub k, we want to show it converges. It's alternating. We see the switch. So if we see an alternating series, unless it's geometric, you definitely have to do the AST. If it's geometric, you could do either. So AST here. So alternating series test. First step, we want to take the limit of A sub k as k goes to infinity. Well, A sub k does not include the switch. A sub k is just this part. And that limit, and now it's true, you can push the limit inside the square root, but there's a better way to do this because that's going to give you L'Hopital's and it's going to be a pain. You could do this. Everything is positive, so you could do this. You can make the top share the same root as the bottom. And so then push the limit to the inside, so you can take the square root of the limit of k to the 4th over k to the 6th plus 1. So that's the best way to take the limit of that, of something that has a square root in part of it but not the other part of it.
So that's the only way to put the limit inside the square root if the numerator and the denominator have square roots, and that way
It's
they go
the only functional way, because you could put it in here, but then you're going to get infinity over infinity, and it's not going to help.
Okay.
Now, if you had a constant divided by a square root, then you could do it.
Okay.
But for us, we want to be able to have something that's not indeterminate. And what's the limit of the inside there? K to the 4 over k to the 6 plus 1?
0.
0. So that checks. That is good. And then second part of the AST, here we want to show that the terms are decreasing. This is, if you use the algebraic approach we've been using, this would be a pain in the neck. You plug in k plus 1 here, and have to raise it to the 6th power. Plug in k plus 1 there, you have to square it. Total pain. So what we're going to do instead is show that the derivative is negative. Because we learned in Calc 1 that if a function's derivative is negative, you have decreasing. If the derivative is negative.
So is the reason why it's serious because did you divide the k to the power 6 from the top and the bottom, so then you're left with 1k because you have to square, that cancels the k squares, and then you plug in infinity and that's how you get to 0?
So you can divide by either k to the 4 or k to the 6. If you divide by k to the 4, the numerator is going to 1, and the denominator is going to have a k squared plus 0. And so the denominator will go to infinity. So we have 1 over infinity, which is 0.
Okay.
Yeah. Why don't we take our break, and we'll finish this one after the break. So just think in your mind during the break, your Calc 1, if you wanted to show a function is decreasing, you show that its derivative is negative. So that's what we're going to do here to show that that is, in fact, a decreasing sequence.
You have 3x squared minus 1.
Maybe even more than half the battle. Okay, let's go ahead and finish off that one with the calculus. Okay. So this is the, when we use the alternating series test, this first thing, finding the limit of a sub k. So for an alternating series, a sub k is this part, does not include the switch. So this is a sub k for an alternating series. This is the divergence test. And if you get a limit equal to 0, it's inconclusive. Just like we've seen a million times with the harmonic series 1 over k diverges. But these terms are going to 0. Right? Those terms go to 0. But that's not enough. Just because the terms go to 0 doesn't mean the series converges. The terms have to go to 0 fast. Not just go to 0, they have to go to 0 fast. And that's what we did with the improper integration, and we sort of saw 1 over x squared converged, but 1 over x diverged. So the power on the x in the denominator had to be bigger than 1 for convergence. So they have to go to 0 for sure, but they have to go to 0 fast if you want convergence. So this just says, okay, they're going to 0. Are they going to 0 fast enough? That's what this next test thing, next piece of the test tells us. If these are shrinking and going to 0, that's fast enough with an alternating series. Now, what we would like to show here, normally we do it algebraically. Normally we do this algebraically by doing this. But that's not going to work with the current example because the power is to the 6th. So if we were to do it algebraically, we would have to put a k plus 1 in there and then raise it to the 6th power, which would be a lot of work. Foil it all out. So they recommend, hey, let's use calculus, because we know from Calc 1, if the derivative of a function is negative, the function is decreasing, because the tangent values are going to be sloped downward. Now, there's another subtlety here. Taking the derivative of this with a square root is a pitta. We would have to do a lot of exponent manipulation, subtract, half down, subtract 1. There's a clever way that we could get at this. If you do this kind of thing that we did over here, if you rewrite this as the square root of k to the 4th over k to the 6th plus 1, if the inside is decreasing, then the function with the square root on it is also decreasing. For a square root function to decrease, the stuff on the inside must also decrease. You must be taking the square root of smaller and smaller and smaller numbers for the overall expression with the square root to decrease. So you can kind of ignore the square root. If we can show what's inside here is decreasing, well then the square root of all those numbers is also decreasing. Okay, so what we're going to do is consider this function. We're we're going to write this function f of x equals x to the 4th over x to the 6 plus 1. If we can show that that's decreasing, then if you put the square root in, it's still going to be decreasing. And so you can convince yourself of that by looking at the square root function. So if you look at a picture of the square root function, to show that this function, like if we're going this way, the numbers are getting smaller. Well, the y values are getting smaller, but also these x values are getting smaller also, right? They're simultaneously going down to 0. Okay, so to show this is decreasing, we're going to take the derivative. The derivative here, we do have to use a quotient rule. So we do the low derivative high. So there's low d high minus high d low, all divided by low squared. So we want to show that that's negative. If we can show that's negative, we are golden. Then we can make our conclusion about the alternating series test. In the numerator, we are going to have 4, if we distribute here, we have 4x to the 9 plus 4x cubed minus 6x to the 9 over x to the 6 plus 1 quantity squared. Okay, we have some like terms. We have negative 2x to the 9 plus, so we factor out, we didn't factor yet, so plus 4x cubed, all divided by x to the 6 plus 1 quantity squared. Now we're going to factor. In the numerator, I'm going to factor out the GCF, so negative 2x to the 3. What are we left with? We're going to have x to the 6 minus 2. That look right? Factoring? Yeah, that's going to be negative. Yeah, I agree with that. Do you agree with that? Okay, so x is going to infinity. X is going to infinity. So we take the limit of f of x as x goes to infinity. Oh, no, I'm not taking the... I shouldn't... let me restate what I just said. We're not taking the limit, but we're thinking about x being large. My point being that when x is large, this is definitely positive always, no matter what. But this is also going to be positive, right? When x is large. You agree that's positive? X to the 6 minus 2? You could find some values of x for which this is not positive, but as long as x is further out, it's eventually true. Right? Maybe you have to ditch a couple of x's. So this is negative. So this leading negative, this is less than 0 for x greater than 2. Greater than or equal to 2. And if you plug in a 1, yeah, not true. But if you plug in a 2, yes, it's true. So if you're bigger than or equal to 2, it's definitely true. Therefore, the sequence is decreasing. Because the derivative is negative. Okay, so our conclusion here is therefore we have convergence for the original series. So the alternating series test tells us that this series converges. That series converges. Now it's got minuses in it. It's an alternating series. So then we have to decide, well, does it converge absolutely or conditionally? So then we take the series of absolute values. So the series of absolute values, we just take away the switch. So it's k squared divided by the square root of k to the 6 plus 1. K is starting at 1, I believe. So that. So now we have to decide if that series converges. If that series converges, then we have absolute convergence. If that series diverges, we have conditional convergence. Well, that series is not in any nice, convenient form, but we could compare it to something pretty easily. So this is our A sub k. We're going to choose a B sub k to compare it to by ditching the 1. If we ditch the 1, that's the most insignificant piece here, then we have this. Well, square root of k to the 6 is k to the 3. So we get k squared over k to the 3. This is 1k, 1 over k. So that is what we're going to compare it to. And does this series converge or diverge? That's a harmonic. It diverges. The terms go to 0, but they don't go to 0 fast enough. We've shown that this diverges with the integral test. So somehow you have to say why it diverges. You can say it diverges because it's a p series and the p-value is not bigger than 1. Or you could say it's harmonic. We've done this enough that this is assumed to be common knowledge by now. So it's totally fine to say that. So our suspicion is that this diverges. That's our suspicion. Let's check. So we would want to show that A sub k is bigger than B sub k. Because bigger than diverging diverges. So that for the direct comparison test to work, we would have to show this. So let's see, can we do that? So A sub k is the original, it's the one that we're analyzing. So if we can show that this is true, we don't know. But if that's true, then we're going to have this is diverging. So yeah, we're moving. Probably it's a long one. All right, so cross multiply. Square both sides. Is that true?
No.
No. So with the comparison, if you get a false there, then we do the limit comparison. So direct comparison test. So this is DCT, direct comparison test. Inconclusive. If DCT is inconclusive, then we go to LCT. So the LCT, we take the limit of A sub k over B sub k as k goes to infinity. So the limit of A sub k, that's the original that we're dealing with here. So k squared over square root k to the 6 plus 1. We divide by B sub k, which means multiply by its reciprocal. And see what we get for the limit. If this limit is a constant, if it exists, then both series do the same thing. So this is the limit of k cubed over this. So once again, when you're doing a limit with a square root, the best way is to square the part that doesn't have the square root and put a square root in there. That's the Calc 1 technique. Okay, and what is the limit here?
Infinity?
Nope.
0.
Nope. Third time's a charm.
1.
1. 1. 1. Right? So the limit is as k goes to infinity. So you can think of it in 3 ways. Polynomials that have the same power, you look at the quotient of leading coefficients, 1 over 1 is 1. Or you could divide everything by k to the 6, and you'll get a 1 here, and a 1 here, and a 1 over k to the 6, which goes to 0. So you get 1 over 1, which is 1. Or you could do L'Hopital's rule 6 times.
No.
No. So regardless of how you do it, you need to get the right limit. So limit is 1. Does anyone not see the limit as 1? I think the easiest way to see it is division by k to the 6th power everywhere. Then the 1 over k to the 6 goes to 0. And these two go to 1. Yeah?
Could you explain again how you went from K to the 30 K to the 6?
So,
Where is it? Or-
so everything is positive. The square root of k to the 6 is k to the 3. So you do this thing where you put a square root in, but you square what's here first.
Oh, right.
And that way you have a square root top and bottom that you can pull to the outside. And then you can zoom in on the inside.
Yeah, I was just dumb and put k to the 9 instead of k to the 6, so it's like, would
Oh,
be
yeah, bigger-
infinity?
Yeah. Hey, okay, and you got, how did you end up with k to the 9? Oh, when you squared this?
I just
Oh, gotcha,
squared the
gotcha,
three, yeah.
gotcha. Yeah, that's easy mistake. Okay, so limit comparison test says if the limit exists, both series do the same thing. So this limit exists, it's a number, it's not infinity, so that limit exists. So therefore, both series diverge. Both series diverge.
So it's conditional.
So it's conditional convergence. So the original series, through a lot of freaking work, converged. But the series of absolute values diverges. So the original series is conditional convergence. Yeah. Conditional. So, first step, you gotta show that the series converges. And then, let's try this one. Alternating series. So let's first show the series converges. So we first do the limit as k goes to infinity of a sub k. A sub k is everything but the switch. And that is 0. So this is the divergence test. In our mind, we say the divergence test is inconclusive, so we can continue. If that limit were not 0, we would be done and we would say diverges. If that limit is not 0, we're done. Now we show that the series, or the sequence of terms, is decreasing. So we want to show, this one we can probably show algebraically. We want to show that as we go further out, the terms are getting smaller. That's what we want to show. That is showing that it's decreasing. You could use calculus. We just did. But usually that's a lot more work. So this is what we would like to be able to show. We do our cross multiplication. And when we cross multiply here, we end up with a log on each side. And it's not dividing out the word ln, even though it kind of looks that way, but we are exponentiating both sides. If you exponentiate both sides, you end up with this, which is true. So we've now done the alternating series test. We've shown that the limit of the terms is 0. We've shown that the terms are decreasing. That's all you need to show for convergence. So therefore, we have convergence for this alternating series. So we have converge. And then once we have an alternating series that we've shown converges, then we decide, is that convergence conditional or absolute? So now we switch our perspective. We come back to the original series. We ditch the switch. And we consider that. So this is the series of absolute values that we now need to consider. And we have to decide whether this series converges or diverges, which we actually just did either last Thursday or Tuesday. Does this one converge or diverge? Does that denominator go to zero, go to infinity so that the fractions go to zero fast? We know that 1 over x, which if you visualize x, that's how fast x is going to infinity, and we know that that's not fast enough, that we need x squared or more. So x is not fast enough. Natural log of x is a bird wing. That goes to infinity even slower than x goes to infinity. So this thing definitely diverges, but how did we show it? With the comparison test to 1 over k. So 1 over k, we know that that one diverges, harmonic. That diverges because it's a harmonic. So we would want to show bigger than diverging diverges. So if we can show that the a sub k's are bigger than the b sub k's, then we're done. Then we've shown divergence. So let's see. So 1 over natural log of k greater than 1 over k. We cross multiply. And this is true. That's true. I guess we didn't do that. That is true. And we've looked at this picture last week. We were looking at these graphs. Natural log is this function. Y equals x is this function. So that is true. K is bigger than natural log of k. So therefore, over here, we have both diverge. Both are going to diverge here. So the series of absolute values diverges. So this convergence is conditional, because the absolute values are going to squish the convergence and make it diverge. So this is going to be conditional divergence. Conditional convergence. Divergence is divergence. It's not conditional or absolute. All right, conditional, absolute. I lost track on all the tests. Is that the 8th one? I know there's 10 total. We're getting close. I think we're at our last 2 tests now. I think. Yeah. All right. Last 2 tests, the root and the ratio test. If you have a good handle on the geometric series, these 2 tests are just consequences of the geometric series. So let me just remind you that the geometric series says the following. I have it right here on the board. If you have a geometric series, if the common ratio's absolute value is less than 1, you have convergence. If it's not, you have divergence. So for a geometric series, less than 1 means convergence. So here we go for the ratio test. This is probably the most important test in terms of tests that you're going to use later. When we get into the next chapter, ratio test is what we use when we have power series. So ratio test is going to be probably the most important one of all of them in terms of using it repeatedly in the future. So the ratio test says this. We've got an infinite series. The a's could be positive, could be negative. If it were an alternating series, a lot of times we pull out that switch and analyze it without the switch. Doesn't matter here because we're going to take absolute values regardless. Okay, so for the ratio test, all we do is take the absolute value of a sub k, put it in the denominator, and we put the next term's absolute value in the numerator. So we form a ratio of consecutive terms. A sub k plus 1 over a sub k, absolute values. If the series is positive, obviously you don't need the absolute values, if everything's positive. Ratio test has the same conclusion as the geometric series. Less than 1 converges absolutely. So if there were minuses in here, you can say that it converges absolutely. If there are no minuses, you could just say it converges. Saying it converges absolutely, even if there's no minuses, is not wrong, but it's just a little overzealous. If the common ratio, or the ratio that you get here, if it's bigger than 1, including infinity, the series diverges. And if you get 1, the test is inconclusive, you go back to the drawing board. You're not done. The question is, why does this test work? The answer is relatively easy to understand. If the limit of this ratio equals r, you can multiply both sides by a sub k, and it tells us that when you go out into the tail of the series, that the next term is about r times a sub k. That's what a geometric series is. The geometric series says to get from one term to the next, you multiply by a common ratio called r. So that's why when you go out into the tail, the series is acting like a geometric series, so we use the same conclusion. R less than 1 converges, R bigger than 1 diverges. So that's it. So let's try our good old ratio test. When you see a factorial, the ratio test is the best test to use 99% of the time. Because your a sub k plus 1 over a sub k will get rid of the factorial symbol. Right? Let's see. Let me prove it to you. So we are going to use the ratio test. So we're going to take the limit as k goes to infinity of the absolute value of a sub k plus 1 over the absolute value of a sub k. So the ratio of consecutive terms. So this is the limit of 2 to the k, took the absolute value over k factorial. That is your, oh, I don't want to put that in the denominator though. Let me rewrite this. I didn't form this fraction carefully. So I want to form it more like this. 2 to the k over, 2 to the k plus 1 over k plus 1 factorial. And then in the denominator, we have the original 2 to the k over k factorial. So we have that. So a sub k plus 1, we replace the k with k plus 1. We take the absolute value, which just gets rid of that negative sign. And then a to the k is in the bottom. Sebastian, question?
Where did the limit of k approaches infinity of the absolute of the numerator and denominator came from?
This is the ratio test.
Oh, that's the rate. Okay.
This is the ratio test. So if we're going to use the ratio test, we do the limit of the ratio of absolute values of consecutive terms.
So k will be substituted by k plus 1?
Mm-hmm.
Okay.
For a sub k plus 1. Yeah.
For the numerator.
For the numerator. Always the numerator.
Okay.
Yes. And then we have limit. We flip the denominator. So the numerator, let's put it like this. The denominator, we're flipping it. So we get that. How many 2's are left over? We have k plus 1 2's in the top. We have k 2's in the bottom. So there's one extra 2 in the top, so they all cancel but 1. All right. Now let's focus on, so we're kind of focusing on these two, and now we're going to focus on these two. How much is left when you have k factorial over k plus 1 factorial?
1 over k plus 1?
1 over k plus 1.
Oh wait, further? I just kind of guessed.
For real, bro!
Because first is k plus 1 and then you have the k factorial outside, right?
Yes, exactly.
Okay.
Right, those cancel.
Okay.
Right? K plus 1 factorial is k plus 1 times k factorial. Your intuition is spot on.
Surprising.
No, your intuition's usually good. You panic though, and then you don't listen to your intuition. So it's so easy in math to sort of have a sense of what's happening, but then get tangled up in the details. Okay, and then what's that limit?
0.
0. Is that less than 1?
Yes.
Yes. Good. Good math. Less than 1, therefore converge. So the ratio test, just like the geometric series, if you get this ratio, and they call it R, so maybe I'll put a little R out in front, R equals. If you get less than 1, you have convergence. It's a pretty, reasonable test.
Is that kind of the same rule when it comes to the p-series as well, or that
P
one-
series is backwards.
Okay.
P series says bigger than 1, you have convergence.
Okay.
Because the P series is focusing on the denominator. So 1 over k to the P, in the denominator, P bigger than 1, you have convergence. But with the geometric series, you're focusing on this exponent, which you're in the numerator. Here, this R has to be less than 1 for convergence. So you've got to be a little careful there, right? They're opposites.
Okay.
So geometric series, less than 1 is convergence. P series, bigger than 1 is convergence. Because the geometric series is in the numerator, and the P series, you're in the denominator. So in the P series, you want the denominator to grow fast so that the fractions go to 0 fast. In the geometric series, you're dealing with the numerator already. And that's it, therefore convergence. Let's try this one. So we're going to take, let's call it R. So R equals the limit as k goes to infinity of the absolute value of a sub k plus 1 over the absolute value of a sub k. To get a sub k plus 1, you just replace the k's with k plus 1. So there's the numerator, a sub k plus 1. Everything's positive here already, so we don't have to. And actually, let me make one point about this last one. This did have negatives. So we could actually say that this is absolutely converging, not just converging. Because that had negatives in it. And we did take absolute values, so we're actually finding absolute convergence there. Here, there's no negatives, so our conclusion, we don't need absolute. All right, so in the denominator, we just write down a sub k exactly as we see it. And then we do our copy dot flip thing, or whatever you say to yourself. Copy dot flip. We've got that. Okay. Again, let's break this up by focusing on the exponentials here and here. How many 4s are left over and where do they live?
1 in the bottom.
1 extra 4 down below, downstairs, in the bottom, in the denominator. Everyone see that? Right, we have k plus 1 4s in the bottom. We have k 4s up top. They all cancel but 1. So we have 1 extra 4 and it's downstairs. So we have this. Now we have the k squared and the k plus 1 squared. There's a couple of things we could do here. We want to pair them together, so I'm going to pair them like this. I'm going to say, hey, let's extract that power and do this. So, combine these two. All right. We can evaluate the limit now. So the limit as k goes to infinity is going to be, tell me in the numerator, what's the limit of that as k goes to infinity?
e to the numerator. It's,
Not quite, because the exponent is not a k.
oh,
I
right.
100% agree if it was k plus 1 over k to the k,
Right.
this is easier. This is going to go to infinity over infinity, but they have the same power, so you end up with
Just one.
1. Right, so when you take the limit in here, k plus 1 over k, you can push the limit to the inside. You could say to yourself it's infinite over infinite, so you'd use L'Hopital's rule, take the derivative 1 over 1 is 1. Or you have polynomials that have the same power, so you look at the ratio of leading coefficients. So whichever way you look at it, you get a 1 up top and a 4 down below. And this is less than 1. Therefore, we have convergence. We don't need to say absolute convergence here because the series has only positive numbers in it. So same conclusion as the geometric series. So if you were to break apart just this right here, you're going to think about the limit of the inside and then square it. The limit of the inside, if you wanted, you could divide everything by k. So you have 1 plus 1 over k to the 2. That limit inside there is 1 because 1 over k goes to 0, so you get 1 squared, which is 1. However you conceptualize it. That's one way to do it. One way to think about it. Okay, let's see. I'll do this one and you guys can do the next one. So R, once again, is the limit of a sub k plus 1 divided by a sub k with absolute values. So the absolute values, in this case, we see some minuses. So we are going to conclude absolute convergence if we have convergence. Now let's talk about some intuition here. In that numerator, if you take away the minus sign, you have 7 to the k, which is an exponential function. In the denominator, you have a polynomial function. So if you think about your growth rates, exponential grows faster than polynomial. The faster one is in the numerator, so we should get divergence. All right, let's see if we do. So we're going to take the limit, and we're going to have 7 to the k plus 1 over k plus 1 squared. Oops, yeah, it's messy. K plus 1 squared. All that's divided by 7 to the k over k squared. So we took absolute values, so the minus sign disappears. So we are going to end up with 7 to the k plus 1 over k plus 1 quantity squared multiplied by the reciprocal of the denominator. So we get that. That's a k. That's a square. All right, starts to get pretty obvious with the constants. We see there's 1 extra 7 in the numerator. And then I'm going to group these square terms together again. So that's k divided by k plus 1 quantity squared. That's a 1 inside there. 1. And what is our limit going to be here?
7.
7. So once again, we have the k over k plus 1, which is 1. 1 squared is 1. So this overall limit is 7. This is not less than 1. Therefore, diverge. All right, so that's it. If that limit is not less than 1, you have divergence.
For the ones with negatives, is it an absolutely converges or a
Yes.
conditionally converges?
It's always absolute because we did an absolute value here. So remember that if a series converges absolutely, it also converges regularly. So when we do these absolute values here, we are
I was thinking
determining
about it
whether it's
backwards, yeah.
absolute or not.
Yep.
All right, you all try this one. So form your R value. By taking the limit as k goes to infinity. Thank you. What's your intuition telling you? Should you be confirming convergence or divergence? When you look at that summation, the factorial is in the numerator, and the factorial grows way faster than a polynomial, which is in the denominator. So you should be, your math should be confirming divergence. You should know that you're going to be trying to get divergence. And when you do your k plus 1, you can start to kind of do this in one step here where you just flip your a sub k. Jump right to that step. This is supposed to be a k plus 1 over here, though. K plus 1 to the 6. So there's a sub k plus 1, and then dividing by a sub k means multiplying by its reciprocal.
Why are we ignoring the negative 1 to the power of k?
We're not ignoring it, we're applying the absolute value.
It's just the switch.
This is either plus 1 or minus 1, and we have to take the absolute value of it, so that makes it positive 1. So absolute value, if you see a negative anywhere, it just disappears when you take this absolute value.
Right, but did we plug in the so you basically plug in the k plus 1 in the numerator of the 1?
Numerator here and denominator there. It doesn't matter if you plug it in here. If this is k or k plus 1, it's still either minus 1 or positive 1. And when you take absolute value of negative 1 or positive 1, you get just 1.
Okay.
So absolute value will always just take away the switch. The switch has no magnitude. It's just 1 or minus 1. It's not adding any magnitude. So when you take the absolute value, it just disappears.
Okay.
But we're not ignoring it. We're applying the absolute value. And then let's see what's left here. So the k plus 1 factorial piece and the k factorial, that's all going to reduce to
K plus 1 in the numerator.
k plus 1 in the numerator. Because k plus 1 factorial is k plus 1 times k factorial. K factorials cancel. So this is going to be k plus 1 in the numerator. And then let's group these things together. So we have k to the 6 and k plus 1 to the 6. So that's all to the 6. And what is the limit of this part here? This whole part goes to 1. Because k and k plus 1 have the same exponents, so the ratio of coefficients is 1. And this piece goes to infinity, so the overall limit is infinity times 1, which is infinity. This is greater than 1, it's not less than 1, therefore diverge. Sebastian?
Yeah, so going back to the question for the -1, when you substitute the k to k plus 1, that so basically it's not there, but theoretically it's still there because when you substitute any number into the k, it's still gonna equal to 1.
So both of these, so when you put in the k plus 1, like that,
It's still gonna be 1
Still be-
because no matter what you put in the k, raised to the power for the 1 is just still gonna be 1.
yeah.
Okay.
No matter what this power is on -1, your answer inside the absolute value is either plus 1 or minus 1. And when you take the absolute value of plus 1 or minus 1, you always get 1.
One.
Yeah. Cool. Time for your last test. The root test. Again, it's just like the geometric series. Now they don't use an R, they use a rho, a Greek R instead, because of no great reason other that they're trying to get you in your mind to think of rho is for root test and R is for ratio test, just as a way to distinguish them. But it's the same. Some books will actually just use R instead. And again, if the series has negatives, we're taking an absolute value. So if we have negatives in there and we get convergence, it's truly absolute convergence. But the conclusion is identical. If rho is less than 1, converge. If rho is greater than 1, diverge. If rho is equal to 1, try again. Inconclusive. Why does this ratio test work? Same idea. If this limit is true, you can raise both sides to the k power, and that just tells you that when you're far out in the series, your a sub k is acting like rho to the k. And so it's like you have common multiplication by rho repeatedly, which is geometric. So if the tail of the series is acting geometric, that's enough to say that it's geometric. Because we don't care about the leading terms. It's the tail that dictates convergence. So both root and ratio are essentially geometric series. Let's try one. When we use the ratio test, typically is dictated when you see factorials. So if you see a factorial, 99% of the time, the ratio test is the right thing to do. When you see a power on the outside, 99% of, well, with the root test, it's less than 99. It's probably more like 90% of the time, go root test. We will see some inconclusive root tests, but when you have factorials, really almost every single time, ratio will work. If you see a power in the outside root, usually like 9 out of 10 times it'll work. But that's the first thing we should do. So the first thing we should do here is form the root test, bless you. So we're going to take the limit as k goes to infinity of the kth root of the absolute value of a sub k. So once again, absolute value. So the effect here is that this kth root of this kth power, those undo each other. So we're going to be left with the limit as k goes to infinity of, let's see, k root of that, and then absolute value of that, we have 2k over k plus 1. So the absolute value takes away that minus sign, and the kth root takes away that power. And what's that limit?
2.
Powers match, You have linear up top, linear down below, so you take the ratio of leading coefficients, which is 2. Or you divide everything by k, does not matter. So you get that? So now we have to remember that we had when we were doing limits in the last section, we had the limit comparison test. And the limit comparison test said, as long as the limit exists, both series do the same thing. Totally different here. We have to conclude based on the geometric series. So it's not just that we get a number here. This number tells us something specific. Less than 1 convergence, greater than 1 divergence. So we've got to be really careful that we don't confuse. This is bigger than 1, therefore we have divergence. So it's not just enough that the limit exists. The value of the limit is super important. Whereas for the limit comparison test, the value didn't matter. If the limit existed, then we had conclusions. So root tests can be extraordinarily fast. Let's take a look down here for the root test. So rho is going to be the limit as k goes to infinity. Kth root of the absolute value of a sub k. Well, there's no negatives here, so the absolute value is meaningless. But the kth root, we just take away both kth powers. So we get the limit as k goes to infinity of k over 2. Which is infinity. Which is bigger than 1, therefore we have divergence. So when you apply the right test, things can go pretty quickly. Now you could use the ratio test here and get to the same answer. It will work. A lot of times you'll have multiple tests that can't work. But we generally try to be as efficient as possible, so when we see a power of k on the outside, start with the root test. That's going to be your fastest. One expression that shows up repeatedly with the root test is the kth root of k. We need to understand how to find the limit of the kth root of k. Here are the terms of the sequence. Here is a visual for the kth root of k. Based on the graph, it's pretty obvious that it converges to 1. Intuitively, it's probably not obvious in your mind. 6th root of 6, 7th root of 7, 8th root of 8, 9th root of 9, 10th root of 10. Like, we don't usually deal with indices that look like that on our roots, so it's pretty hard to conceptualize in your mind. But if you look at the graph, it makes sense. How would we calculate this mathematically? How would we find that limit? There's a process that we have done for evaluating limits that involves a logarithm. Log limit process? Do you remember that? So if we rewrite this as a function like that, kth root of k, right, is the xth root of x. Then we take the log of both sides. And when we take the log of the right-hand side, we can pop the exponent down. And then we take the limit of both sides as x goes to infinity. And on the right side, we're hoping for L'Hopital. Can we use L'Hopital on the right? We have infinity over infinity.
Yeah.
That's L'Hopital. So by L'Hopital's rule right here, we have infinity over infinity, so we're going to take derivatives. Derivative of the top is 1 over x. Derivative of the bottom is 1. And what's the limit of 1 over x as x goes to infinity?
0.
This is 0. So on the left side, we have natural log. So we have to exponentiate both sides. So the limit of y is going to be e to the 0, which is 1. So that's how we show it using the log limit process, that that limit is 1. Okay, so where is that going to show up? Oh, right here. Oh, shocking. So we are going to do root test again. We see this, we don't have a power of k on the outside of the whole a sub k, but we see a power of k right there. And so, and we now know that the kth root of k is going to have a limit of 1. So let's see what happens. So we're going to take the limit as k goes to infinity, kth root, absolute, a sub k. We have a series that has no negatives, so the absolute value is redundant, don't need it. So we're going to have limit kth root of k over e to the k. So this is going to be the limit of the kth root of k divided by e. And so where does that limit equal?
Less than 1.
So it's 1 over e, right? The k through to k, that limit we just showed is 1. So we get 1 eth here, 1 over e. This is less than 1, therefore converge. Now, there was no absolutes in here, there's no negatives in here, so we can say that's all good. We don't need to say absolute convergence, that's redundant. Series only has positive numbers, so it don't need it. All right. Yeah.
So the k square of k will equal to 1?
The kth root of k's limit is 1. The kth root of k's limit is 1. So the limit of the kth root of k as k goes to infinity is 1.
And that's because we were able to prove that because of that.
Yep. Yes.
Okay.
So that proves it mathematically, and then this proves it visually.
Okay.
That if we look at this sequence of terms, they're getting closer and closer to 1. There's 1. Make sense?
Mm-hmm.
All right, good. All right, let's try another one. So this one has a slight snag. So we're going to take the limit as k goes to infinity, k through to absolute a sub k. We have to use some ingenuity here. The absolute value is the part that I want you to think about. So certainly the kth root part just ditches that k from the outside, but I want you to think about the absolute value in here for a moment. So the kth root part takes away that power of k. The absolute value bars here matter. If you think about your k's, isn't this denominator always negative? If k starts at 1, 1 minus 5 is negative 4, 1 minus 6 is negative 5, etc. Or whatever the next term is, 1 minus 10 is negative 9. What is the absolute value of 1 minus 5k? Can anyone think of a clever way to evaluate that without getting gnarly by going to a piecewise defined function?
5k minus 1.
100%. The absolute value of a minus b is the same thing as the absolute value of b minus a. And if one of the directions is always negative, then the other direction is always positive. Correct? If you plug in 1 here, 5 minus 1 is 4. If you plug in 2, 10 minus 1 is 9. Now it's always positive.
And also, just once we get to the limit, we don't care about the 1 anyway.
True.
So you can just make negative 5k positive.
Yeah, that's...
The 1 is so...
Ooh, wait, say that again, Erica?
So if you left it as 1 minus 5K, but then you get to the limit,
You're gonna end up with a negative limit though.
I guess I'm doing it this way, but just like thinking about it rather than doing it.
Yeah, if you left the minus out here, that would give you a limit of negative 1/5 instead
But
of
then you
positive
take
1/5.
the absolute value there.
You could do that. That's true. You could do that.
And it's still less than 1 anyway.
It's like the magnitude is less than 1. Yeah, that would
Well,
work.
Negative 1/5 is still less than 1 too.
That's true. That's not what we mean though.
I know.
Because negative 2 is less than 1, but that would give us divergence. So be careful with that one. What was that, Brianna? Okay, so what's this limit?
It's 1/5.
Which is less than 1 and therefore converge. Now, this had minuses in it originally, right? This is minus in here when you plug in your k, so we're going to say converge absolutely. So there we want to include that absolute stuff because we have negatives. Oh, let's just take a glance at this. So this one, you have to choose your test. We'll do this on Thursday. We see factorials, we're going to go ratio. We see powers, we're going to go root. So we'll do that on Thursday. And then on Thursday, we'll get to chapter 11 with the power series. The most important chapter
Do you have
of them all.
a sheet together of like
Yes.
what you like if you see something that's the test you should use?
Yeah, so choosing your convergence test, so I kind of summarize it here at the beginning of section 8.
Okay.
Because there's 10 of them.
I'd like to be able to like study like if you
Yeah.
see the factorial, you use the ratio test.
Yes. Factorial is ratio, power is root, and then there's all the other ones.
And then if you don't see anything that you
Alternating
recognize,
alternating series test. You know, like you want to be able to recognize a P series, an alternating series, a geometric series. The one that people seem to not recognize instantly enough is geometric.
geometric, yeah.
Geometric seems to be a little subtle for some reason. But when you think geometric, you think power.
Yeah.
So geometric, you know, think that there's the powers on the outside. The K is on the power, in the power group.
I can't really do any homework if I'm gonna
Wait, what's your excuse for not doing homework?
So I forgot my charger today, and then I was gonna use it to also look notes for my class,
Oh, yeah.
and I forgot my charger at home. So from
Is
here,
there a cable on the wall outside?
that area, so I know that over there has like the iPhone charge, Samsung chargers, and all that, but I don't think that uses it because I think I did it on my iPhone, and it wasn't charging her.
Oh, really?
Yeah.
That's a fail.
But I mean, I'll do it when I get home with my charger. You know?
Yeah. For sure. Anyone have questions? Stick around. I'll do math with you.